Hello everyone, this is Kiran Kumar. I hope everyone saw the previous problems related to 1D bar cases, and today I am going to further solving the next type of as well as next complicated models. Okay, the next one that I am going to do today is which is on these are all the previous problem contents. Uniformly distributed load. Okay, so the previous two problems what we solved is on a point load. Okay, and a further extension that can be do by taking the other types of loads, that is uniformly distributed load, where which is usually denoted by W, acting over the element. Okay, so how that load is converted and that is applied for a particular element. Okay, that case I am going to solve today with the what is the equations related to that, and later on how that can be implemented to the problems. Okay, so let's see. Directly I am going to show you the equation related to that. Okay, so this is the equation. W is equal to WL by 2 and WL by 2. So this one indicates it is a if I take it is a single element which is consisting of two nodes, the whole uniformly distributed load that is being applied to the node 1 and node 2. Okay, that's what the meaning is. See, we know that distributed load is always along the length of the bars. Okay, so since I cannot use the whole bar element to take the load, that's why I am distributing that load into the each node. Okay, so let's go for some example and then I'm going to explain that. So this is a small example that I'm going to take in which this arrow mark indicates the UDL. Okay, and its magnitude is given. Okay, that's what W here. Okay, W refers to the magnitude of the particular UDL. So how will you judge that? By go through the units. So this is a W value that is provided in the problem. So how will you do that? So the first thing is, as usual, you are going to discretize this. A simple discretization consisting of a single element, node 1 and 2, along and displacement 1 and 2. Okay, this is what the simple discretization part. In practically for this case it is not good, but let's see, discretize with a single element, that's it. So after that, how I can find out the distributed load? By using the regular equation, where I have to go through the load equation WL1 by 2 and WL1 divided by 2. Okay, means this one okay, so the meaning is here this load is applied to the node 1 and this load is applied to node 2. Okay, that is what the meaning. So like this we are going to solve the actual problem, okay, of the UDL. That's it. I hope everyone getting this point. So based on this, let us go for the problem. So this is the actual problem where the displacement and stresses I need to calculate for this problem, where he is already defined that I should use two finite element models. Okay, and Young's modulus is given as 200 GPa, and the other factors which is provided here, that is its thickness. Okay, its thickness, and then the length 0.3 0.1 meter on the top end and the bottom end, as well as the load magnitude 200 kilonewton. This is a point load. You just closely observe how I judge this as a point load, because it is 200 into 10 raised to 3 Newton. Okay, so thereafter, in addition to this load, I am having one more load, okay, and which is along the length of the bar. So that's why which can be considered as a uniformly distributed load. And look into the unit, that is 25 into 10 raised to 3 Newton per meter. So by considering the unit also, you can judge that it is a UDL. Okay, so after considering this, the next thing is the two cases which is included here, where the first portion is the UDL part, and the second portion is the conversion of the whole tapered bar. This is actually a tapered bar. I cannot solve this by using the regular finite elements. So I should solve this by discretizing this. Okay. So there are two new techniques that you are going to learn from this problem. One is conversion of this tape into stepped bars, and the second one is how to apply this UDL. Okay. So these two things you need to you are going to learn from this problem. Okay. So in exam they may ask these two cases in a different question itself. Okay. Yes. Since he said that I should use the two finite elements I have to use, so then I'm going to discretize this by two elements of length 1 meter. Okay, of length 1 meter, and the equivalent model. So if I discretize this into two stepped bars in this way, so what is going to happen is in this way, I should calculate the area of the first bar. This is the first bar, and calculate the area of the second bar. Okay. Like this, I need to calculate for the element 1 cross-sectional area, element 2 cross-sectional area. So how will you do that? By using our previous case of the Hypermesh lab, okay, where we initially calculated the average area. Okay, so that is what which is provided here. Our average length here I am going to provide. How will you do that? 0.3 plus 0.1 divided by 2. This gives you the average length. Sorry for that. This gives you average length. Okay. And then this length I am going to substitute for the first one, that is 0.3 plus 0.2 by 2, 0.25 meter, and here 0.1, this 0.1 plus 0.2, this 0.2 divided by 2. If I multiply these values with the thickness, I am going to get the cross-sectional area. Okay, the same thing we did for the Hypermesh lab also. Okay, so first step is how we are going to convert this into stepped bar. First step is calculate the average area or the average length, and then consider that average length mean by taking the first length, that is 0.3 plus average length divided by 2. Next 0.1, the second length, and then plus average length divided by 2 is equal to some values. Okay, if I multiply that with the thickness, I am going to get the cross-sectional area. Okay, this is how you have to convert a tapered bar into stepped bar. So I got the what we call the average areas. Okay, area of the first bar, this is the first bar, and then area of the second bar. Okay, so like this. Once I did this, after that I can do the finite element model for this. Okay, how will you do that? With the elements. Okay, right now the what we call the coordinates, it is in downward directions. It may be in any direction, so no need to worry. Coordinates in downward directions. Two elements I consider. First element for this cross section, second element for this cross section, and later on, how many nodes? 3 nodes. Okay, 1, 2, 3. Where node 2 is shared by element 1 as well as element 2. Cross sectional area of the area 1, area 2, I need to calculate. Okay, just multiply by thickness to this part. Okay, so what about length of this element 1? That is 1 meter, as well as the length of the element 2 is also 1 meter, because the total length is 2 meter. Okay, so first you have to calculate all these. So area 1 is 0.25 into 0.05, where he multiplied the thickness. Okay, similarly 0.15 into 0.05, multiplying thickness, I am going to get the cross sectional area. Since what we call the Young's modulus is 200 GPa, so for both elements that value is common, 200 into 10 raised to 9 Newton per meter square, and length is also 1 meter, as I said. Next thing is stiffness matrix for the element 1. How will you do that? So simply by using the regular equation u sub x1 7 is equal to a1 u1 divided by l1 1 minus 1 minus 1. So here I am going to get it as substituting all the things. So one thing you need to be note down is the previous problems that I did in an mm², but here I am using all the units in meter square, because the load magnitude is in 25 kilonewton per meter. Okay, either you can convert that load, that is W, that is either you can convert this load or take all the units in meter only. Okay, so I am doing the first case. Okay, what is the first case? Converting or maintaining the units of meter only. Okay, so both cases you can do. So I am going to maintain in meter right now for this problem. So 0.0125 into 200 into 10 raised to 9 divided by length of the element. So that I am going to get it as some number 2.5 into 10 raised to 9. So immediately you have to do the node numbering. Okay, since this is related to the first element, which is comprises of node 1 and node 2. So node 1 for the first column, node 2 for the second column. Similarly, node 1 for the first column, node 2 for the second column. Okay, like that. So once do the node numbering, that is degrees of freedom, let's go for the second stiffness matrix. So that's where I'm going to get as substituting A2, E2 and L2. A2 is 0.0075 meter square. I'm maintaining meter square as a common unit. E2 200 into 10 raised to 9 divided by length of the L2, that is 1 meter. So if I am going to substitute all these, I'm come across it 1.5 into 10 raised to 9 and minus 1 minus 1 1. And coming to the node numbering scheme, so here the element 2 comprises of the two nodes, that is 2 degrees of freedom, that is actually u2 and u3. So 2 refers to the first 2 refers to the first column, 3 refers to the second column, 2 refers to the first row, 3 refers to the second row. Okay, so once I substitute these two, the one thing you need to be worry is regarding the numbers 2.5 into 10 raised to 9, 1.5 into 10 raised to 9. Since the numbers are different here, okay, while calculation of the global stiffness matrix, you need to multiply this to the matrix, that is 1 into 2.5 into 10 raised to 9. So I am going to get it as 2.5 into 10 raised to 9 minus 2.5 into 10 raised to 9 minus 2.5 into 10 raised to 9 and 2.5 into 10 raised to 9. Here 1.5 into 10 raised to 9 and minus 1.5 into 10 raised to 9 minus 1.5 into 10 raised to 9, 1.5 into 10 raised to 9. Okay, like this only you have to do. Okay, let's come to what we call the distributed load calculations for each elements. So that is UDL. Okay, so if I observe the problem persisting of UDL. So let's calculate the load because of that UDL. So we know the equation WL1 divided by 2 WL2 by L1 by 2. So W, we know that it is 25 kilonewton per meter, where I am maintaining Newton per meter as the unit. Okay, and length as 1 meter, 25 into 10 raised to 9. That 10 raised to 3 I am going to take it as common. Okay, this is related to W only. Okay, W in terms of Newton per meter. And similarly, WL1 divided by 2, 25 into 10 raised to 1 divided by 2. So if I do that part, simplify that, I'm going to get as 12.5 into 10 raised to 3, 12.5 into 10 raised to 3. And similar to the previous cases, here also I have to do the node number. First row refers to the node 1, second row represents the node 2. Okay, coming to the next element, for the element 2 also, the number subscripts is going to change, WL2 divided by 2, WL2 divided by 2. So I'm going to get, if I substitute all these things, once again I'm going to get the same values, but the only difference is about the node number. Okay, here it starts with the node 2, element 2, and node 3, that is element second node. Okay, so like this, node numbering is important. Okay, once you did this, the next part is consideration of global load vector. Okay, so along with these loads, if you observe, we are having one more load which is at node 3. Okay, one more load at node 3. So here, so that load also I need to consider during calculation of global stiffness, global load vector. And what about global displacement vector? It is nothing but, since we are having 3 nodes, 1 to 3, global displacement vector will be U1, U2, U3. So here it comes with the global displacement vector. And coming to this global force vector, as I said, it is 12.5, where I should do the summation for the each nodes. So I am going to show you here how that value arises. So if global force vector is F, so I know that the 3 force terms should be there. That is 1, 2, and 3 on each node. Okay, at node 1, so you need to observe these load conditions. We are having only one node, one value, 12.5 into 10 raised to 3. Okay, so the power you can take it as a common outside. At node 2, we are having 12.5 from the first element and 12.5 from the second element. Okay, that is also, I will judge that by looking into the number, node number, this one. So 12.5 plus 12.5, that is 25. Okay, 25 into 10 raised to 3. Okay, coming to the node 3, we are having only one value that come across with the element 2, but along with this we are having point load also. Okay, so I should judge or consider that one also, that is 12.5 plus at node 3 we are having the load magnitude as 200 into 10 raised to 3. Okay, So that should be 200. Whole multiply by 10 raised to 3. Okay, so like this the global force vector will arise. Okay, so the best thing about this one is you have to look into the node numbers from each load diagram. Okay, so so I got the global force vector also. Coming to the global stiffness matrix. So for the global stiffness matrix, so the same thing. So there is all the related things. Yes. In order to find out the global what we call stiffness matrix, you should once again come across this one. So since the numbers are changed, I am going to multiply the values. So it is 2.5 minus 2.5 minus 2.5 2.5 1.5 minus 1.5 minus 1.5 1.5. Okay, so from the first element I am going to get only 2.5, that is 1 1, and minus 2.5 2 1. So and if I look into this, I don't have any 3 1 relation from both elements, so that's why it is 0. So since it is symmetric, at the same value I'm going to copy here as well as this one. And at the node 2 we are having 2.5 from the element 1 and 1.5 from the element 2. So I should do the summation here, 2.5 plus 1.5. Okay, and 3 2 connectivity, we are having only one value from the element 1 2 minus 1.5, from the element 2 this location it is minus 1.5, and from the element 2 3 3 relation is 1.5. so I got the global stiffness matrix also, where 10 raised to 9 I kept outside. So once you get this 3 cross 3 matrix, okay, so the next part is maintaining the equation in terms of f is equal to ku, already defined here. So k, so this is the k matrix, and this is u matrix, that is equal to f. Okay, so this is how you have to go for ku format. That is what the global equilibrium equation that I already shown here. So once you did this, the next part is applying the boundary conditions. Boundary conditions, we know that node 1 is completely fixed, that is u1 equal to 0. Since u1 equal to 0, by using the elimination method, so the particular row and particular column has to be terminated. Okay, if you did that, the remaining matrix will be a 2 cross 2 matrix. Okay, remaining matrix will be a 2 cross 2 matrix. So once again, if you perform the matrix multiplication, finally we are going to get u2 equal to 0.095 mm and u3 equal to 0.237 mm. Okay, so that two equations you finally are going to get along with this. Okay, so once you did that, the next part is calculation of the stresses. Okay, so stress in the element equations are similar to compared with the previous one. That is sigma 1 is equal to E1 divided by L1 minus 1 1 U1 U2, where U1 value is 0, U2 value you substitute and maintain the units in mm. In order to get it in megapascal, I am maintaining unit in mm. That's it. Okay. Similarly, stress in element 2, E2 divided by L2 minus 1 1 U2 U3. So why it is U2 U3? Because it consisting of two element node 2 and node 3. Here it is node 1 and node 2. So substitute all the values. Okay. So that is in mm I substituted. That's why I'm maintaining units in units of Young's modulus and length in mm also. Okay, so that I'm going to get these two values and the stresses that is generated in the particular elements. So I hope you will practice this session. So from this session we are learned two things. Okay, so one is how to convert this tapered bar into a stepped bar, and the second part is how to apply the UDL load. Okay, so these two things we learned in the present problem. I hope you are going to solve this and ask for any queries related to this problem. Thank you everyone.